This is the second video in BC Calculus on convergence and divergence tests. We've previously looked at the nth term test, which can help us determine divergence, but in terms of determining convergence, we have not really found any test that can work to our benefit just yet. So the first one that we're going to look at to determine convergence is the ratio test. Now, ratio tests can only be used on geometric series. So a geometric series is a series where the terms, there's a common ratio, like multiplying by 2 to get from term to term, or multiplying by 1/3, which would be like dividing by 3 to get from term to term. If that's the pattern in the series, then that's a geometric series. Those geometric series are going to converge based on the value of that common ratio, and it's the absolute value of it. So even if it's a negative amount that you're multiplying by, we don't pay attention to the negative. If the absolute value of the common ratio is less than 1, then we can use the ratio test to prove that the series would converge. However, it will diverge if the absolute value is greater than or actually equal to 1 for the common ratio. And then if a geometric series converges, a lot of times you'll be asked to find the sum of it. And we discussed in the previous video, the sum formula for a geometric series is a sub 1, so the first term, divided by 1 minus that common ratio. So we're going to look at some examples here of when the ratio test could be used and how it would show us convergence or divergence. So looking at this particular series right here, I look at it and I can immediately tell that this is a geometric series because it has that variable being in the exponent component to it with that 2 to the n in there. So the first thing that I would do is I would write out some terms of this series because I'm going to need to be able to determine the common ratio in order to move forward with determining convergence or divergence. So start by substituting in whatever that first n value is that they told you to start with. So that would be 3 over 2 to the 0. 2 to the 0 is 1, so my first term is 3. And then move up by increments of 1. So the next number that I would substitute in would be n equals 1. So that would be 3 over 2 to the 1, or 3 over 2. And you could keep going if you wanted to see some more terms. But in terms of finding my common ratio, I only need the first two terms because we do second divided by first. So that becomes 3/2 times 1 over 3, or 1/2. I then immediately know that this number is less than 1, so I can say, therefore, the series from n equals 0 to infinity of 3 over 2 to the n converges by the ratio test. And then since it does converge, they wanted us to find the sum of it. So the sum would be the first term, which is that 3 that I found, divided by 1 minus the common ratio. So that's 3 divided by 1/2, or 6. So if I wrote out an infinite number of numbers that followed this series pattern and added them together, they would eventually converge to a value of 6. All right, so I want you to pause the video and see if you can make any sort of determination on this example right here. Okay, so hopefully when you wrote out your first two terms and then divided them to find the common ratio, you saw that you had a common ratio of 3/2, which is greater than 1. Therefore, this series would actually diverge and not approach a particular sum value because r is greater than 1. And notice my explanation that I wrote out. That should be what you're writing on your paper too, with the test that you use and why you know that it diverges. So another thing that we use ratios for is to determine the radius or the interval of convergence for a particular series. So notice here in this series, not only does it have n values in it, but it also has a variable x. Depending on what numbers we put in for that variable x, that will determine whether this would be a geometric series that converges or a geometric series that diverges. So what they're asking us to do when they want us to find the radius of convergence is figure out what interval of x values can I choose from to substitute into this summation formula to end up with a series that would actually converge to a common sum. Well, in order for it to converge, we need our ratio to be less than 1. So what we do is we need to come up with the ratio and set that less than 1. But we don't use first term, second term like we did in the last two where we had a specific formula with all numbers in it and the only variable was an n. When you have x's in there, you actually need to find the nth term and the n plus 1th term. So the n plus 1th term, so we can call that a sub n plus 1, that would be this formula, but wherever you see an n, you replace it with n plus 1. So this would be x to the n plus 1 over 4 to the n plus 1 times n plus 1 to the 4th power. That's the a sub n term, or a sub n plus 1 term. The a sub n term is n substituted in. So it's actually the exact way that the formula looks already. So the common ratio then would be, since we can do it with any two consecutive terms, it would be the a sub n plus 1 term divided by the a sub nth term. And it's possible, depending on the formula, that those might actually be negative numbers. So remember, we say that the absolute value of that common ratio has to be less than 1. So we put that absolute value around it because sometimes we do actually need it. Now, with that dividing, I already have a sub n plus 1 as a fraction and a sub n as a fraction. So rather than writing a fraction over a fraction, I usually go ahead and just rewrite my a sub n plus 1 term. That would be n plus 2 there. 4 to the n plus 1. N plus 1 to the 4th. And then I go ahead and do my whole keep, change, flip thing with the a sub nth term and multiply by its reciprocal. Okay, so now this is where your algebra skills come in. I have these two fractions that are being multiplied together, but they have a lot of like terms that I can actually maybe cancel out or at least simplify with. If it helps you, kind of group the things that go together. So like I have an x to the n plus 2 in the numerator, and I have an x to the n plus 1 in one of my denominators. And the way multiplication works is it doesn't matter which fraction it's in, top times top, bottom times bottom. And then I have a 4 to the n in a numerator and a 4 to the n plus 1 in the denominator. And then I have an n to the 4th in the numerator and an n plus 1 to the 4th in the denominator. So I find it helpful to do it like this and kind of group those like terms together. So in terms of simplifying those, when you have a common base like x here that's being divided, we can subtract those exponents. Well, n plus 2 minus n plus 1, that's all just going to become a 1 right there. So this guy's going to be gone entirely. So the first piece just ends up with an x. Same thing here, 4 to the n over 4 to the n plus 1. If I do n plus 1 minus n, that's going to make that go away. And so I just have a 4 in the denominator. Now, this guy is a little bit different. Because the n's are inside the exponent like that, there's not really anything I can do at this point to simplify these terms. The whole point of a series, though, is that we should end up with an infinite number of terms. So we actually want the nth term to end up going all the way to the infinite term. So what you then want to do, once you kind of reduce that common ratio, is you want to do the limit as n goes to infinity of whatever that simplified thing is. So that would be x into the 4th over 4 times n plus 1 to the 4th. Okay, so now I'm just thinking about, I'm doing the limit as n goes to infinity of this guy. So if I'm doing the limit as n goes to infinity, go back and think about in behavior models with limits to infinity. This would be my highest degree term on the top. And on the bottom, if I was to actually multiply out n plus 1 to the 4th, or n plus 1 times n plus 1 times n plus 1 times n plus 1, my highest degree term would be an n to the 4th with that 4 that was in front. Okay? That then, the n to the 4th over n to the 4th is going to end up canceling, and so we end up with the limit as n goes to infinity of x over 4. Well, notice I don't have any n's in there anymore, so it doesn't matter what n's going to. This just ends up being the absolute value of x over 4. So that is my common ratio for an infinite series. But in order for my series to converge, I want that common ratio to be less than 1. So now you take that simplified common ratio and you're just going to solve that absolute value being less than 1. Now the way absolute value works is that if we take the absolute value off, it should be less than 1, but it should be greater than the opposite of that. It should be greater than negative 1. And now we just solve for x. So multiply 4 to both inequalities. And so our interval of convergence is that as long as I choose an x value between negative 4 and positive 4, then this series, way back here at the beginning, so if I choose a number anywhere between negative 4 and positive 4 to put right there, then I would end up with an expression for a series that will converge because its common ratio will be less than 1. Now, this is going to feel like the problem that never ends. But it's also possible that maybe using these exact numbers, negative 4 and positive 4, will also allow my series to converge. So what we have to do, and I'm going to add another page in, is you have to actually check your endpoints. So what you do is you say, well, what if x was negative 4? Well, if x was negative 4, then my formula would be the sum from n equals 1 to infinity of negative 4 to the n plus 1 over 4 to the n times n to the 4th. And so you would want to test the convergence of that guy. So I could start with n equals 1, find my first term and my second term, and just see if that common ratio would be less than 1. So if we substitute 1 in for n, I end up with negative 4 to the 2, so that becomes 16, over 4 to the 1 would be 4 n to the 4th. Oh, n is 1, so that would be 1 to the 4th, so that goes away. So my first term is 4. If I substitute 2n, I end up with negative 4 to the 3rd, so that's negative 64 over 4 squared, which is 16, times 2 to the 4th, which is another 16. So that ends up being the number negative 1/4, I believe. Okay, and so then remember the absolute value of our common ratio would be negative 1/4 divided by 4, or negative 1/4 times 4 over 1, which is equal to 1. Notice if it equals 1, then that diverges. So we do not include x equals negative 4. And then we do the same thing with x equals positive 4. That would be the sum from n equals 1 to infinity of positive 4 to the n plus 1 over 4 to the n times n to the 4th. Write out the first two terms. So if you substitute 1n, 4 squared would give you 16 over 4. So again, that would be a value of 4. And then substituting 2n, 4 cubed would give us 64 over 16 times 16. So we would get a 1/4 there again also. So that common ratio would be 1/4 divided by 4, which we already know from above, gives us a value of 1. So that guy also diverges. So that takes us back to the original problem, where I know that those two numbers are not included in my interval of convergence anymore. So this is my interval of convergence. The radius then is end minus beginning divided by 2. So 8 over 2 is 4. So my radius of convergence is 4. I said 4 and wrote 2. And my interval of convergence is from negative 4 to positive 4.